So I have a ball, and because I didn't want to use a normal moment of inertia equation, I went ahead and gave you a moment of inertia of 0.53 mr squared. The mass of the ball is 1.7 kilograms and a radius of 0.29 meters. And I'm going to roll that ball from rest, from a height of 2.24 meters down to the bottom. And I'm going to assume that no energy is lost due to friction and the ball is rolling without slipping when it reaches the shaded part of the image. And I want to know what is the velocity of the ball when it reaches that flat shaded part. And so this question, we need to worry about both gravitational potential energy and translational kinetic energy, but we also need to worry about rotational kinetic energy. So at the beginning, we have gravitational potential energy. And at the bottom, we're going to have both translational kinetic energy. So that's the fact that it's moving to the right. But we're also going to have rotational kinetic energy. And we're going to have rotational kinetic energy because it is rolling. So because the ball itself is rotating about its, it's rotating, then I want to make sure that we also account for that energy that is in the rotation. So in the beginning, because it's not moving, we have all gravitational potential energy. There's no translational or rotational kinetic energy. And so at the bottom, at this point, we're going to say that that's a height of 0. So that way, my gravitational potential energy is 0. But there will be both translational and rotational kinetic energy. And I know that translational will be more than rotational. And so I went ahead and drew it like that. Now, how much it is on the left side for my gravitational potential energy should be the same as if I added these two together. So I need to make this a little bit taller and that a little bit taller. And then that's going to be about the same. So now what I can do is I'm going to write my equation. So I'm going to start with gravitational potential energy. That's mg times delta y, or in my case, I like to use h. And kinetic energy and rotational kinetic energy will be 0. So I'll leave those as zeros. And then the gravitational energy, potential energy at the bottom will be 0. My translational kinetic energy is 1/2 mv squared. And my rotational kinetic energy is 1/2 I omega squared. Now, what I'm going to notice is that, first of all of the terms have a mass in them. Oh, but a moment of inertia doesn't. It's hidden in there. So what I need to do is I need to go ahead and substitute in for moment of inertia, so that way this cleans up a little bit. All right, so now I can see that all of the terms have a mass, so I'm going to go ahead and divide mass out from all of these. Now I have G, I have the height, I have mass, but I don't know velocity and I don't know angular velocity. And so this can be a problem unless I remember the relationship between these. So one way that I like to remember it is that my angle here and my radius, if I multiply those together, I get the arc length, which I like to think of as x instead of s, but you could think of it as s or x. And then angular velocity times my radius is going to be translational velocity, and angular acceleration times radius is angular acceleration. Oops, sorry, translational acceleration. So I'm going to take this angular velocity times radius is equal to velocity. And what I'm going to try to do here is I want everything in terms of velocity and not angular velocity. So if I rewrite this equation and put it so I know what angular velocity is, I divide both sides by my radius, and I get my angular velocity is equal to my tangential velocity divided by r, which means that if I say, oh, well, then I want to know what angular velocity squared is, then that means that I need to square the top and square the bottom, so I'll have v squared over r squared. So this then can go here instead of omega squared. Now, I recognize that I could have done it the other way, and I could have substituted in velocity and put in angular velocity. But the reason why I like to do it this way is then you can see that the radiuses cancel out. And then it makes the math a little bit easier. So now I will have GH is equal to 1/2 times my velocity squared plus 1/2 times the 0.53 and then times v squared. So I went ahead and added these together. Because these are both v squareds, I'm able to add the number in front of them, just like if I was going to add 3x plus 5x, I would get 8x. It's the same idea, but now I'm doing it here with v squareds. So I have 0.5 plus the 0.265, and so that gives me the 0.765. And the v squared part stays the same. And then I went ahead and substituted in g and h. So g will be 10. My height is 2.24. And then I have that 0.765. So all I need to do is divide both sides by the 0.765. And then I'm going to square root both sides to solve for v. And I get an answer of 5.411 meters per second, and that will be my velocity at the bottom. So it is going slower because it is not only moving, but it is also rotating. If you have any questions, let me know.